Hey, good morning, everyone. Today, we are going to discuss tutorial for chapter 3, which is the convection. Okay. Okay, for the first question, which is the flow of hot oil over a flat plate. Engine oil at 60 degrees Celsius flow over the upper surface of a 5-meter long flat plate whose temperature is 20 degrees Celsius with a velocity of 2 meter per second. Okay, determine the total drag force and the rate of heat transfer per unit width of the entire plate. Okay, before we start answering all this first, okay. So here you have the temperature and then the velocity. Of course, you have the length of the flat plate and then the surface temperature, which is here. So I mean the unknown is the surface area here, AS. Okay, the question asks you to find what is the total drag force and the rate of heat transfer per unit width. Of course, when you want to find the area, area is equal to length times width. Okay, solution. Engine oil flows over a flat plate. The total drag force and the ratio of the heat transfer per unit width of the plate are to be determined. This first, okay. Assumption. The flow is steady and incompressible, where we determine that we use the critical number for this flow. Okay, this critical Reynolds number is equal to 5 times 10 to the power of 5. And then the property of the engine oil at the film temperature of Tf equal to Ps plus T infinity divided by 2. I mean, how can we get this solution? This formula is that based from the small notes, the small books. Okay, you can refer to that. Okay, so we want to find the properties of engine oil at the film temperature. So Tf here we get 40 degrees Celsius. Then after that, we want to find all the properties. We refer to table A13. So here is the table of A13 here. Okay, engine oil here. You can see at the bottom here. Okay, so at 40 degrees Celsius, we have here, this is the density, and this is the specific heat, this is thermal conductivity, this is thermal diffusivity, dynamic viscosity, kinematic viscosity, Prandtl number. Okay, so we focus on this, the film temperature. Okay, from there get this is what density, this is the thermal conductivity, this is the Prandtl number, and then this is 2.485 is actually here kinematic viscosity here. So after that, we want to find the Reynolds number. Okay, so SL is 5 meter. So we substitute everything, the value for each variable, which is v, this is the velocity, this is the length, and of course this is kinematic velocity, to find the Reynolds number. So we get 4.024 times 10 to the power of 4, which is less than the critical Reynolds number. So which means that for this type of flow of the engine flow over the flat plate is actually a laminar flow which is less than 5 times 10 of power of 5. So from there, okay, you can get this coefficient here. So CF equal to 1.33 REL. Okay, power of negative 0.5, so substitute everything, you get 0.00663. Okay, so after we get the value for the CF, okay, noting that the pressure drag is 0 and thus the CD equal to CF of parallel flow over a flat plate. The drag force acting on it is, by using this formula, actually all this value can be obtained from the question. So we substitute everything, we get 58.1 Newton for the drag force. Okay, the total drag force acting on the entire plate can be determined by multiplying the value obtained above by the width of the plate. This force per unit width corresponds to the weight of mass of about 6 kg. Therefore, a person who applies an equal and opposite force to the plate to keep it from moving will feel like he or she is using as much force as is necessary to hold a 6 kg mass from dropping. Similarly, the Nusselt number is determined using the laminar flow relation for a flat plate. So Nusselt number equal to HL divided by K equal to 0.664, REL 0.5, P Prandtl number power of 1/3. So this is 0.664 times. This is the Reynolds number that we have calculated before. This is the Prandtl number based on the property here. So we get the Nusselt number is equal to 1913. So after that, we can easily find the H value, the heat transfer coefficient. Okay, so we get 55.25 watt per meter square Kelvin. So after that, we can just substitute. Okay, Q equal to HAS times T omega T infinity divided L minus T surfaces, so equal to 55.25 times 5 times 1 meter. So this is what we assume the width of the plate. So this is the surrounding and this is the surface temperature. So we get 11,050 watt for the rate of heat transfer. Okay, so that's answered the first question. So we move to the second question. This question is a little bit long. Okay, here a little bit. Heat dissipated from an engine in operation can cause hot spot on its surface. If the outer surface of an engine is situated in a place where all leakage is possible, then when leak oil comes in contact with hot spot above the oil auto ignition temperature, it can ignite spontaneously. Consider an engine cover that is made of a stainless steel plate with a thickness of 1 cm and a thermal conductivity of 14 watt per meter Kelvin. The stainless steel plate is covered with a 5 mm thick insulation, which is the thermal conductivity is K equal to 0.5 watt per meter Kelvin. The inner surface of the engine cover is exposed to a hot air at 350 degrees Celsius with a convection heat transfer coefficient of 7 watt per meter square Kelvin. The 2 meter long engine outer surface is cooled by air blowing in a parallel over it at 7 meters per second in an environment where the ambient air is 60 degrees Celsius. To prevent fire hazard in the event of oil leak on the engine cover, the engine cover surface should be kept below 180 degrees Celsius. It has been determined that 5 mm thick insulation layer is not sufficient to keep the engine cover surface below 180 degrees Celsius. To solve this problem, one of the plant supervisors suggested adjusting the blower capacity to provide an increase in the cooling air velocity by 10%. Determine if this is a viable method of keeping the engine cover surface below 180 degrees Celsius. Evaluate the air properties at 120 degrees Celsius. So, the question is really quite long. Okay, consider an engine cover that is made by stainless steel. So this is the engine cover. The thickness here D is equal to 1 cm, where K is equal to 14 watt per meter Kelvin.